right, welcome to practice problem 2 from week 14. So as always, let's start by reading the problem and trying to understand what's going on. So we are told that a water park wants to add a new attraction called the Tarzan Swing, where guests will stand on a platform, swing while holding a rope, then jump into a pool of water below. We're told that the platform on which the rider stands when they start to swing is 5 meters above the lowest part of the rope during its swing. The rope is 25 meters long and is connected to a steel beam in the ceiling. For safety reasons, the ride must be able to safely support people up to 150 kilograms. And what we want to know is how much force must the beam to which the rope is tied be able to withstand. So let me just sketch this and write down what I understand of this problem from what I'm told, because it'll be easier to look at this actual situation. So there is a platform. There is my platform. Person stands here, and they hold a rope that is attached to the ceiling. And that rope is going to swing along a circular path. Let's try to get this. There we go. That right there looks like it is the middle of the rope. And at some point here, the person is going to jump off. And so underneath that, down here somewhere, will be the water to catch the person. So this is how I understand the situation. And let me exaggerate my circle a little bit here to make my sketch a little bit easier. There we go. Okay. So what are we told? We are told that the platform right here is 5 meters above the lowest part of the swing. So let's call this, let's call the initial height, let's call this 5 meters. And then let's call, so this will be our time 1, is when the person is standing on the platform. So time 1 will be the person at rest on the platform. And time 2 is going to be where the force the rope exerts on the beam, which is also the force that the rope exerts on the person, because Newton's, that's how ropes work, is greatest. Because I want to find how much force, the maximum force, the beam is going to have to withstand. So where on this arc is the force the rope exerts on the beam going to be the greatest? Well, it's going to be where the person is moving the fastest. And the person will be moving the fastest down here at the bottom. So let's make that, it's not really a circle. It doesn't really matter, but it bothers me. There we go. It's going to be right here. So that's going to be time 2. So time 2. So the person is moving at the bottom of the circle. And it says the person jumps off, and I don't really care where the person jumps off. Doesn't matter to me if the person jumps off after that midpoint, if they jump off before. What I want to know is the maximum force that is going to be on that beam. Because if the beam is going to break, it's going to break when the force is maximum. And so that's when the person will be at the bottom, regardless of where they jump off. Them jumping off is irrelevant to this problem, because that doesn't affect the force exerted on the beam. So the height of the person in time 2, I'm going to make this my 0 point. I'm going to do that so that there is no gravitational energy at the bottom. It's all kinetic energy. That way my equations look a little bit nicer. I could make both of these non-zero. I could set the height of the water to be 0, and then this would be like 10 and this would be 15. But that at that point I'm just adding more terms to my equations that don't need to be there. So I'm going to leave this as my y0. Remember, I'm always free to pick where my height of 0 is for myself. We are told that the mass of the person, the maximum mass of the person is going to be 150 kilograms. That's like, I think that's like 325 pounds. And that's just because they want this to be able to support basically anyone. So that is their maximum mass that they are allowing on this ride. So if the beam will not break for someone with 150 kilograms, it will not break for anyone less than that either. So that is why they pick such a large mass, I suspect. Is there any other information that I'm given that I haven't used yet? Yes, I have not included the length of the rope. And the length of the rope, if I look at my sketch here, the length of the rope defines the radius of my circle. So I can say the radius of the circle is going to be 25 meters. So now, let me write down sort of what I know from this. So the person is not moving on the platform. They are at rest on the platform. So that means that V1 is equal to 0. I should put my velocities here. So the person is moving at the bottom of the swing. Do I know how fast that person is going? We are not told that, so I'm just going to put a question mark there. So it's a thing that I can find, but I don't know what it is right now. So here's my follow-up question to that. Why? Why is this person moving at the bottom of the swing? So there are a number of ways that we can answer this. I can answer this in terms of forces. There's a force exerted on the person that is causing them to accelerate. However, when I'm moving in a circle, talking about acceleration and forces in that way, especially when I'm moving in a circle at a non-constant speed, which we know because the the speed starts at 0, ends at not 0, so we know it's accelerating. So talking about forces and acceleration, talking about kinematics in a circle, is very difficult. So I could go down that road, but to make my life easy, I'm not. What I'm going to talk about instead is energy. So the person is at rest on the top above where they started. So what I can say is the person starts with gravitational energy that as they go downwards is transformed into kinetic energy. So this is a transition from gravitational energy to kinetic energy. So maybe I can use this to help me find how fast the person is going at the bottom. Now, why would I care about how fast the person is going at the bottom? So we want the force exerted on the beam. And if I think about my rope here, if I think about my rope at the bottom, the beam is pulling up on the rope. This is the force the beam exerts on the rope. And the person is pulling down on the rope. And how should these two forces compare to each other? Well, if the rope is a single solid object, it's not really accelerating. So I'm going to say the sum of the forces are equal. And I am treating the rope as if it has no mass. I am simplifying this. So my assumption is the sum of the forces on the rope is 0 because the rope has no mass. Therefore, I don't need to consider the mass of the rope. I'm going to make that assumption because they didn't tell me the mass of the rope, and therefore I don't think I need to use it. So I might want to explicitly say this. So sum of the forces on the rope is 0, and therefore the force the beam exerts on the rope, which is ultimately what we want to know, because by Newton's third law, the force the beam exerts on the rope is equal to the force the rope exerts on the beam. That's going to be equal to the force the person exerts on the rope. which also by Newton's third law is equal to the force the rope exerts on the person. So, I should probably be writing on the entire page instead of just in the corner here, but that's okay. So, how do we find the force the rope exerts on the person? Let's get that all the way over there. Well, the person is moving in a circle. So if the sum of the forces on the person points towards the center of the circle, then the acceleration of the person is going to be the sum of the forces on the person divided by the mass. That's Newton's second law, is going to be v squared over r, because circular motion. So, is this true? Is that true? So let me draw a force diagram for the person when they're at the bottom of the swing and see if this is an equation that I can use. Remember, never use an equation before checking that it actually works for what you're trying to do. So this is going to be my force diagram for person. I should probably label this as time 2. At time 2. So the person is moving that way. But remember, when I'm drawing a force diagram, the velocity does not matter. The direction the person is moving doesn't matter. What are the objects exerting forces on the person? Well, there's the rope, obviously, because we've been talking about the force the rope exerts on the person. There's also the earth. So the force the earth exerts on the person will go straight down, because it always does. And the rope, the force a rope exerts always points along the rope. That's the force the rope exerts on the person. I'm drawing it bigger because this person is moving in a circle. The acceleration is probably going to point towards the center of the circle. So the sum of the forces should probably point up. So does the sum of these forces point straight up towards the center of the circle? And it looks to me like yes, it does. The sum of these forces is going to be the force the rope exerts on the person minus the force the earth exerts on the person. Both of those are vertical, and therefore the force will be vertical. So my answer to is this true is going to be yes, I can. So now I can use v squared over r as the acceleration of the person at that point along the path. And so I need to know the v. So I said that this is a conversion from gravitational to kinetic energy. So let me draw an energy bar chart. So energy bar chart for, and my system is going to be the person and the earth. Whether I include the rope or not doesn't matter. The rope always exerts a force perpendicular to the path the person is moving along. Therefore, the work done by the rope is 0. So it doesn't matter if I include it or not. It has no mass, so it doesn't contribute any kinetic energy. So I'll just leave it out. But if I included it, nothing would be different. So this is going to be from time 1 to time 2. It's going to be time 1. It's going to be time 2. And let me start off with all of my energies, just as good practice. So, is there kinetic energy in time 1? Well, I said the person was not moving, so no. So there is no kinetic energy. Is there gravitational energy? Yes. Their height, their y is above 0, therefore there's gravitational energy. Let me give them 2 boxes. Is there elastic energy? We are assuming the rope does not stretch at all, so there will never be elastic energy. Now, is there any work done from time 1 to time 2? Again, the answer here is no. The force the rope exerts is always perpendicular to the direction the person is moving, and therefore the work done will be 0 because the cosine of 90 degrees is 0. Is there kinetic energy at the end? Yes, there is. Is there gravitational energy at the end? We have defined the height of the bottom of the swing to be 0, therefore no. There is still no elastic energy because there's nothing in the system which can store elastic energy. And we can say that, air resistance, friction, all of that is negligible, so there is no increased internal energy, which means that the kinetic energy, there must be 2 boxes of it. All of the gravitational energy becomes kinetic energy. So if I write this, let me get my subscripts. 2, 2. I can see that UG1 is equal to K2. And now this is something that I can solve. So to find the gravitational energy, that's the mass times G times the height at position 1 is equal to 1/2 times the mass times the velocity at time 2 squared. And what I want to find from this is the velocity at time 2. So the velocity at time 2 is going to be, these masses are going to cancel, square root of 2 times G times Y1. I'm going to use G is equal to 10 to make my life easy, 10 newtons per kilogram. So this is going to be 2 times 10 newtons per kilogram times 5 meters. Nope, 5 meters. So this is square root of 100. Let me check the units here. So newtons per kilogram is, let's add the extra meter in there, kilograms, meters per second squared times meters divided by the kilograms on both sides. Those cancel. Those become meters squared per second squared. When I square that, I get meters per second. So my velocity is going to be 10 meters per second. Okay? So that is the velocity of the person at the bottom of the swing. So the velocity, let's say speed, because I'm not talking about direction. So the speed of the person at the bottom is 10 meters per second. Does that seem reasonable to me? Well, this is a swing that I was going about 5 meters, which is 15 feet. So if I'm going 15 feet down, yeah, I think I would be going pretty fast. That it is a ride. We do want it to be exciting. So that doesn't seem too high. It doesn't seem too low. The units check out, and it is consistent with all of my representations. If all of the gravitational energy is turned into kinetic energy, then this equation works, and this is what we get. So I am okay proceeding from here. So now, I can find the acceleration and force. So the acceleration of the person is equal to the sum of the forces exerted on the person divided by the mass. Sum of the forces, all the way back up from my force diagram, is the force the rope exerts on the person minus the force Earth exerts on the person divided by the mass is equal to, and because it's a circle, v squared at time 2 over r. So this is because we're moving in a circle. And again, I've already checked that this is an equation I'm allowed to use. The sum of the forces does in fact point towards the center of the circle, and that's when I can use this equation. So because we're moving in a circle. All right, and at this point I can just plug everything that I know in. So the force the rope exerts on the person minus the force the Earth exerts on the person divided by the mass is equal to, Oh, I'm just rewriting the exact same thing. So the way I'm going to find the force the Earth exerts on the person, I'm going to use m times g. Again, this is the approximation that we can use when we're close to the surface of the Earth. And this is not that exciting a ride that they're going all the way out into space. Divided by r. I can start to plug my numbers in. So the force the rope exerts on the person minus 150 kilograms times 10 newtons per kilogram. Please no. Divided by 150 kilograms is equal to 100 meters per second squared. Please no. Divided by 25 meters is the radius. Is equal to, multiply both sides by 150. So I get 150 kilograms times 100 meters per second squared divided by 25 meters, and then add the, I'm just going to do this math right now. 150 times 10 is 1,500. 1,500 Newton per kilogram times kilograms is just newtons, which makes sense. This is a force. So the force the rope exerts on the person is, I have to actually use my calculator for this. 150 times 100 times 100 divided by 25 is 60,000 newtons plus 1,500 newtons. So the force the rope exerts on the person would have to be 61,500 newtons. So one thing that I'm going to do for my sake for evaluation is I'm more familiar with pounds, so I'm just going to see what that is in pounds. So 61,500 newtons in pounds. Thank you, Google. Google lets me down. 500 newtons in pounds. That is 13,825.75 of force. So that is a decent amount. But does it seem unreasonable for a ride like this? Again, a person is falling 15 feet on the end of a rope. So I would expect that that rope would have to pull pretty hard on them, that they would have to pull pretty hard on the rope to not fall. So yeah, I think that that seems reasonable. Again, I have double checked that I can use all of the equations that I've used. I have double checked all of my math. 2 times 5 is 10. 10 times 10 is 100. Square root of 100 is 10. So this is the force that the steel beam has to withstand. So if I really wanted to evaluate this again, what I would look at is, the strength of steel. Since I am doing this at home, I have the internet, I can look at, is that a reasonable amount of force for something to be able to support? And looking at what I can find, the answer is yes, that is more than something that is more than the force of steel beam would be capable of supporting. It is a high force. I think that this ride is a little bit extreme. I think the 5 meters is very high. The 25-meter long rope is very high. This is a 75-foot long rope that you are swinging on. So like this is more like a bungee jumping than it is just a slide. So I'd be a little bit concerned to ride this myself, but I am not concerned that my physics is the problem. I think that this is just a very, very adventurous ride. So to just summarize, the beam must be able to withstand a force of 61,500 newtons for the ride to be safe. And the other thing to keep in mind when we're talking about this force is that, remember, this is set for a 300-pound person, for a mass of 150 kilograms, not 300, like 325-pound person. So if a person with like 50 kilograms of mass, which is more average, 50 to 60 kilograms, this force would be like 3 times less. So again, this is the maximum force that it has to exert. So this seems okay to me. I don't see any problems here. I have checked. I've made sure that the sum of the forces that I've written is consistent with my force diagram. And again, don't just assume that these things are consistent because you wrote them both. Always check for consistency. There are 2 forces, one going up, one going down. There are 2 forces in my equation. One is positive, one is negative. Those match each other. In my energy equation, there are 2 bars, 1 in time 2, 1 in time 1, 1 in time 2. And there are 2 terms in my equation, one on the time 1 side, one on the time 2 side, gravitational energy, kinetic energy. So I've actually checked that my representations match the math that I did. I've shown all of my units. I never actually showed my units here. I should probably do that as well. So this newtons I explained, but let's make sure that this gets us the right unit. So kilograms times meters per second squared divided by meters is kilograms meters squared over meters second squared. Please stop. Ooh. So this cancels with one of those. We get kilogram meters per second squared. And that is, in fact, what a newton is. So both of these are in newtons. So all my units check out. I checked that my equations work. I've checked whether the numbers are reasonable to me. So I am convinced that if I have made a mistake here, it's not one that I'm going to catch. I have checked this to the best of my ability. All right. Thanks for watching.